Okay, so in this video, we discuss subtopic 4.3 and 4.4. 4.3 is about force on a moving charge in uniform magnetic field. What does it mean is that if you have a uniform magnetic field, like in this example over here, let's say this one is B and it is going out of the page and it is uniform. And then if you have an electron, which is the charge, passing through the uniform magnetic field, you will expect that the charge will experience some force due to the magnetic field. So to calculate the magnitude of the force, you can use the formula of F equals to Q V cross with B. Okay, this one actually, this is a scalar product. Sorry, this is cross product where V and B both are vectors and the resultants will be in vectors as well. So if you have a cross product, you will have a sine theta. Okay, the product is cos theta. Where Q here is the charge. So if you use electron like this example, then the charge would be E, 1.6 times 10 negative 19. You can write this one for electron. Will be 1.6 times 10 negative 19. And then velocity, normally it will be given. How fast does it travel across the uniform magnetic field? Then the B is the magnitude of the magnetic field itself. And the theta there, okay, is the angle between V and B. Like in this example, you can see that this one is actually the magnetic field is going out of the page and the velocity is to the right. So like in this example, the theta here would be equals to 90 degrees. Okay, so sine 90 is equal to 1. That one would be the maximum force experienced by the charge. Okay, how to determine the direction of the force? Since the force is a vector, you need to determine the direction of the force. Okay, in your lecture notes, you have how to use the Fleming rules. But in this example here that I show you, I'm going to show you how to use what I call a slack rule. Yeah. The advantage of this one is that you don't have to use two hands. You can use one hand only. And for me personally, it is much simpler because you can use for 4.3 and 4.4 when we are dealing about force on a current carrying conductor. Okay, for this example, all your fingers there, like 4 fingers there, will be pointing towards the magnetic field. Okay. Direction of the electrons or the charge would be your thumb. This would be your V. And the force experienced is in this direction if it is positive, and then if it is negative, it will be in that direction, opposite. So basically a back slap. So it's for negative charge. So you only have to use one hand, which is your right hand. Let's write it down over here, right hand. And then point your velocity with your thumb, direction of the charge with your thumb, the magnetic field with your fingers, and then you basically slap whether it's to the front or back hand. If it's a negative, you just back slap it. If it is to the, positive, you just slap it to the front. Okay, if you want to try, okay, this is just another example. So basically, if it is slapped to this direction, it will be a positive charge. It's a positive slap. This one is backhand, it's a negative touch. We hope you guys can remember this. And then this is the examples. Maybe you can try to do the examples to determine the direction of a force. So example A here. Okay, for this example, if you want to do, again, just put all your fingers, maybe you can put your thumb first. So your thumb will be directed in that direction. Okay. And then all your four fingers, the remaining four fingers, is directed towards the magnetic field. Yeah, try my best to draw. So this is your B, this is your V. Make sure you point your fingers, your thumb is straight, L shape. So because this is a positive charge, right? So you have to slap it to the front. So in this case, if you slap it, it goes into the page. Okay. So maybe I change that one instead of cross. Like that. So this is the direction of force because it is positive. So you can write down direction of force is into the page. Okay, and then next example, maybe we can try version B just now. I think I will skip B because that one, the diagram is not really, I didn't really like the diagrams. Anyway, for C, if you want to solve this one, okay, again, point your thumb in V direction. So thumb will be in that direction, right? And then all your fingers will be pointing according to the magnetic field, which is pointing into the page. Not sure whether I can draw it properly. So this is your four fingers, but into the page. Hopefully you can see this. Hopefully you can imagine it. Right. So it's going into the page. So your hand, if you slap it, because this one is a negative charge, so if you want to slap, you have to backhand. Basically this will be your hand, right? So it will be backhand. No, the hand will be. So the force will be in that direction. So force is directed to the left. Okay, we try another example. So okay, maybe two more examples. Okay, let's try to look at question B here. They give you current carrying conductor with a magnitude of current I, and then they ask you to find the force acting on the charge over there. Okay, so if you straight away want to use the set rule tool, you didn't have any magnetic field yet, so you have to determine the direction of magnetic field. You can determine that by using right hand grid rule. So the method to solve this one, first determine B direction. Okay, what you need to do is that you have to put your fingers, your thumb, in the same direction of current. Okay, if you're not sure, you can watch the previous video. And then all your fingers will be directed like that. Okay, make sure you put all your thumb, your thumb on the current directed to the current direction, and then all your remaining fingers will be pointing towards the magnetic field. So in this case, you can see that the region that matters is over here, because this is where the electron sit. So over here, the magnetic field is going into the page. Right. So if, let's say, the electrons are sitting down here, it is actually going out of the page. The magnetic field over here is out of the page. But you don't want to bother over here, you just want to focus over there. I try to redraw it so that you guys can see it. I just write it down. B into the page. Only at this region. Okay. So I just redraw this one. Oops. Okay, and then the electrons is over here, and B is going there. Okay, now just have to use like previously we did. So magnetic field going into the page, thumb is going downwards. So if I want to draw my hand, this is all the 4 fingers going into the page, right? So this is your hand, and then since this one is negative, so you have to backslap it, so it will be directed to the left. Force is to the left. Okay, last example. I think this one is very similar to the previous one. Okay, where they didn't give you any direction of magnetic field, but again you have to do that first. You put your thumb on the current there, so it will be pointed upwards, like your thumb. And then all your fingers in that particular region will be pointing into the page, equal to. So if you have a magnetic field into the page over there, if you're using right hand slide rule, so your thumb pointed in that direction, all your fingers into the page, it's a positive charge, so F will be in that direction. So in this case, force is upwards. Okay, hopefully this one helps, and then you can try to compare with the one in the lecture notes example, and then see whether it's tally up. Okay, the next part is about circular motion of charged particle in uniform magnetic field. Okay, so if you have a uniform magnetic field, and then you have a charge that is coming towards the magnetic field itself, so as it's travel, once it goes into the magnetic field region, it will start to experience a force. And let's say at this particular position, okay, you can see that, I think this one I changed to positive particle. Okay, so let's say if a positive particle, and is at that particular position, the V is going to the left. So if you are doing if you want to determine the direction of force, we see that this one is actually going upwards. Okay, kalau tak okay, dengar balik yang tadi. So this one is going upwards, the force, and then as a result, this one will start to bend. Okay, and at this particular position, if you want to determine the direction of force, when the velocity is upwards, so it's positive, again it will pointed to the center of the circle. And similarly, as it goes here, you can see that eventually it will create a circular motion. Okay, so even if you have a negative particle, it will still create a circular motion itself, it will create down there lah. Oops. So the force will always be towards the center. And if you guys still remember, last semester we learned about circular motion, where summation of Sc is equals to mv squared over r. That means all the force that is towards the center is equals to mv squared over r. So we only have one force there, which is Fb equals to mv squared over r. So Fb, if you guys go back to the initial slide just now, it will be QVB sine theta mv squared over r. And the angle between the velocity and the magnetic field, this is the magnetic field B, it is actually will always be 90 degrees. Okay, you can take a pen, okay, take a pen, put it in that direction, and then put your magnetic field into the page. The magnetic field will always remain into the page regardless of the position, and V will only move left and right. So the angle between them will always be 90 degrees. Because of that, this one becomes 1, sine 90. I cancel out the V, one of the V. I can write down in terms of R equals to mv over qb. Okay. So if they ask you to find the radius, you can use this formula and then solve it. Okay, and here represent the mass of the charge. If it is electron, you have to use mass of electron. If it's some kind of different charge, use that values. Okay, and I choose this charge lah. Okay, this one we already discussed up there, so no need. Okay, in terms of period, so if you guys still remember chapter 2 last semester, V equals to 2 pi r, sorry, maybe I skip one step, V is equals to displacement over time. If you are talking about one complete circle, for one complete circular motion, so I can write this one, V is equals to 2 pi r, because S is equals to 2 pi r over period t. Okay, now I can rearrange in terms of t, which is equals to 2 pi r over v. But I want to substitute my r inside here, which is mv over qb. So it becomes mv over qb. Cancel out the v, and you will left with 2 pi m over qb. Okay, so this is how to calculate the period. And then if they ask you to find frequency, you can simply calculate 1 over t. Okay, now moving on to the 4.4. So I erase because this one is from the notes. I don't want to use this method. Okay, 4.4 is about force on a current carrying conductor in a uniform magnetic field. So what does it mean? Let's say if I have a uniform magnetic field, copy again this diagram. Okay, so if you have a current carrying conductor sitting on a uniform magnetic field, this current carrying conductor will experience force because, if you guys still remember, current exists because there's a motion in charges, there are changes in charges. So that means my electron is moving in that direction. So this electron actually experiences the force. As a result, the whole thing experiences the force, but the force will be opposite. Because direction of current is opposite to the direction of the electrons just now, right? So we are using right hand slide rule to determine the direction. Later on I will show you how. Okay, but you just have to follow using how to determine if it's a positive charge or something like that. Okay, first, before that, we want to focus on the equation. The equation now is equals to F equals to I L cross multiply with the magnetic field B. Because this is a cross multiply, this one becomes sine theta. Again, theta is the angle between I and B. B is the magnetic field, I is the current, L is the length of the conductor. L length. Okay, and then if you want to determine, you can use right hand slide rule, but use exactly the same when you try to determine the positive charge. So I just want to take the diagram here. That one before I erase, and that's why the wording came out. Okay, this is the picture just now. Okay, again, maybe I have to erase this part first. Oh, I think this one is okay. Okay, so your thumb is pointing with the current direction. Your fingers is towards the magnetic field. Okay, so fingers yang banyak tu kan, you can imagine that that one represent magnetic field yang banyak sini. Okay, so this is now ingat this method. Okay, the palm is the force. So we only use slap yang ke depan saja. Okay, in this case, kalau example saya tunjuk ni, the force will be pointing downwards. Okay, because your fingers is pointing into the page, your thumb is pointing to the left. I try to draw the hand. I think by now you guys should be okay code. Okay, this is your B. This is your B. So your force will be downwards. Okay, this is an example. Okay, question, this is an example. Determine the direction of the magnetic force exerted on a current carrying conductor in following cases. So you have current going upwards, magnetic field going into the page. So if I want to determine the direction of force, you put your thumb upwards, okay, all the four fingers into the page. So your force, this is your hand, right? This will be the direction of my force. So for A, to the left. Okay, for B, again, similar diagram, except now the thumb is pointing downwards. This is your magnetic field. So your force is now to the right. Okay, so this one is actually question number 10 from your tutorial. So we try to do one example here. Figure 4.4 shows a conductor carrying current I in a uniform magnetic field B. Show the force due to the magnetic field on the conductor. So they want to determine the direction of force on the conductor due to magnetic field. Okay, so the magnetic field is going into the page. If they didn't give you any direction of current, you can determine by looking at the circle here lah. It's positive, so positive to the negative. So on the conductor itself, this is the conductor, right? The conductor itself, current is going downwards. So if you use the right hand slap rule, okay, your four fingers will be pointing into the page because the magnetic field is into the page. Okay, and your thumb will be directed towards the current direction. So your force will be to the right. So they ask you to show. So maybe you can redraw that part, the conductor itself. So the force is to the right. Okay. And then just to be sure, maybe you can write it down as well. Force to the right. And then the last part, question B, they ask you to calculate the magnetic force on this wire. So it says that the length is 12 cm, 0.12. I change to meter. The angle theta is equals to 40 degrees. And then magnetic field strength B is equals to 0.2 Tesla. Okay. And then the current of 5 ampere. If you want to solve this one, you can use the equation of F equals to BIL sine theta, B is 0.2, 5, 0.12, sine 40 degrees. Okay. Point 2 times 5.12 times 740. So I got here 0.077 Newton. Okay, and then the direction is to the right. Okay, that's it. Thank you.